Have you ever watched footage of a precision-guided missile striking a target the size of a window from a distance of several kilometers and wondered how an object traveling at several times the speed of sound through turbulent air against a target that may itself be moving can arrive at a specific point in space with an accuracy measured in meters or even less? The achievement seems almost miraculous when considered against the background of everything that is working against it. The aerodynamic forces that buffet the missile throughout its flight, the atmospheric density variations that alter its trajectory in unpredictable ways, the thermal stresses that threaten its structural integrity, the vibration environment that would destroy most precision instruments, and the fundamental challenge of navigating autonomously through three-dimensional space without any external reference points or human guidance once the weapon has left its launcher. And yet, modern precision missiles routinely achieve circular error probables, which is the radius within which 50% of shots will land, of less than 10 meters for long-range systems and less than 1 meter for terminal phase-guided weapons. Understanding how this precision is achieved requires examining each of the physical and engineering systems that contribute to it, because missile accuracy is not the product of any single technological innovation, but the result of multiple complementary systems that each address a different source of error, and that together produce a level of guidance performance that would have been considered impossible by the engineers who built the first generation of guided weapons in the middle of the 20th century. The foundation of missile guidance accuracy is the inertial measurement unit, which is the sensor suite that tells the missile where it is, how fast it is moving, and in what direction it is pointed at every moment throughout its flight. An inertial measurement unit contains accelerometers that measure linear acceleration along 3 orthogonal axes and gyroscopes that measure angular rotation rates around 3 orthogonal axes, and by integrating these measurements continuously from the moment of launch, the missile's onboard computer can reconstruct the complete history of its motion through space and compute its current position, velocity, and attitude without any reference to the external world. This self-contained navigation capability is what allows a missile to fly in complete radio silence, immune to jamming, through clouds and darkness, over terrain that provides no visual reference, and still know where it is with sufficient accuracy to guide itself to the target. The physics of inertial navigation is elegant and well understood, but the engineering challenge of building an inertial measurement unit that is simultaneously accurate enough for precision guidance, robust enough to survive the extreme shock and vibration of missile launch, small enough and light enough to be carried inside a tactical weapon, and reliable enough to operate without maintenance or calibration throughout the storage and operational life of the missile is one of the most demanding instrument design problems in all of applied physics. The accelerometers in a high-performance missile inertial measurement unit have to measure accelerations that range from the near-zero accelerations of the coasting phase to the hundreds of G experienced during launch. And they have to do this with a noise floor low enough that the integrated position error over the full duration of the flight remains within acceptable bounds. Modern accelerometers for missile applications use a variety of physical principles to achieve this combination of dynamic range and sensitivity, including electrostatic suspension of proof masses in vacuum, vibrating quartz crystal resonators whose frequency shifts in response to applied acceleration, and micro-electromechanical systems fabricated using semiconductor manufacturing techniques that achieve micrometer-scale mechanical tolerances in a package smaller than a fingernail. Each of these technologies offers different trade-offs between performance, cost, size, and survivability, and the selection of the appropriate accelerometer technology for a given missile application depends on the required accuracy, the available volume and mass budget, the severity of the launch environment, and the cost constraints of the program. The gyroscopes that measure rotation rates are equally critical to the guidance accuracy and equally challenging to engineer for missile applications. Traditional mechanical gyroscopes use the angular momentum of a spinning mass to resist changes in orientation. But their moving parts are vulnerable to the shock and vibration of missile launch, and their performance degrades over time as bearing wear introduces friction and wobble. Modern missile guidance systems use ring laser gyroscopes or fiber optic gyroscopes, which have no moving parts and measure rotation rates using the interference of laser light traveling in opposite directions around a closed optical path. When the path rotates, the light traveling in the direction of rotation takes slightly longer to complete the circuit than the light traveling against the rotation. And this timing difference, measured through the interference pattern of the two beams, is proportional to the rotation rate with extraordinary sensitivity. These optical gyroscopes can detect rotation rates of millionths of a degree per second. They are immune to the gravitational effects that degrade mechanical gyroscopes. They have no moving parts to wear out or fail under shock, and they can be manufactured in packages small enough to fit inside a tactical missile. The combination of ring laser or fiber optic gyroscopes with microfabricated accelerometers has produced inertial measurement units that are smaller, lighter, more accurate, and more reliable than anything that was available to the first generation of missile designers. And this improvement in inertial sensor technology is one of the primary drivers of the increase in missile accuracy over the past several decades. Despite the advances in inertial sensor technology, pure inertial navigation still accumulates errors over time due to the fundamental physics of integration. Every measurement contains noise, and when noisy measurements are integrated to compute velocity and position, the noise accumulates as a random walk whose standard deviation grows with the square root of time. For a long-range missile with a flight time of several minutes, the accumulated inertial navigation error without external correction can be tens to hundreds of meters, which may be acceptable for some applications, but is insufficient for precision strike missions where the required accuracy is measured in single digits of meters. The solution to this problem is the integration of additional guidance modes that provide external position fixes at intervals during the flight, allowing the inertial navigation system to be reset to a known accurate position and preventing the error from growing without bound. The most common external guidance modes used in modern precision missiles are satellite navigation, terrain contour matching, and active or semi-active homing seekers in the terminal phase, and each of these addresses the inertial error accumulation problem in a different way that is suited to different phases of the missile's trajectory and different operational environments. Satellite navigation, using signals from the GPS constellation or its Russian, European, and Chinese equivalents, provides position fixes with typical accuracies of 1 to 3 meters anywhere on Earth where the satellite signals can be received. And these fixes can be applied at any point during the missile's flight to reset the accumulated inertial error. The integration of satellite navigation with inertial navigation is not as simple as replacing inertial measurements with satellite measurements when the latter are available. The two systems have complementary error characteristics that make them much more powerful in combination than either is alone. Inertial navigation provides smooth, continuous, high-rate position and velocity estimates that are not affected by signal outages or jamming, but accumulate error over time. Satellite navigation provides absolute position fixes with bounded error that does not grow over time, but the fixes are available only when signals can be received, are subject to jamming and spoofing, and have a measurement rate that is too slow for the high bandwidth control loop of a maneuvering missile. A Kalman filter, which is a mathematical algorithm that optimally combines measurements from multiple sensors with different noise characteristics and update rates, continuously blends the inertial and satellite navigation data to produce a position and velocity estimate that is more accurate than either sensor could provide alone, and that degrades gracefully when satellite signals are lost rather than failing abruptly. Terrain contour matching is a guidance technique that uses the missile's radar altimeter or other sensors to measure the terrain elevation profile beneath the flight path and compare it to a stored digital terrain map to determine the missile's position. The terrain elevation profile of any given ground track is essentially unique, like a fingerprint, and by correlating the measured profile with the stored map, the guidance computer can determine where the missile is with an accuracy that depends on the spatial resolution of the terrain map and the precision of the altimeter measurements rather than on the accumulated error of the inertial system. Terrain contour matching is particularly valuable for missions in environments where satellite navigation signals may be jammed, or where the mission planning requires the missile to fly at low altitude to evade radar detection. Because the terrain following flight profile that is already required for radar evasion naturally generates the terrain elevation data needed for the contour matching navigation. The limitation of terrain contour matching is that it requires distinctive terrain features to provide accurate position fixes. Over flat, featureless terrain like open ocean or desert, the terrain elevation profile provides little useful information for position determination, and the system falls back on pure inertial navigation. The terminal phase of the missile's flight, which is the final few seconds before impact, when the missile is close enough to the target to use sensors that can directly detect and track the target itself, is where the most dramatic accuracy improvements come from and where the guidance technology is most diverse and most rapidly evolving. Active radar seekers, infrared imaging seekers, electro-optical seekers, semi-active laser homing, and millimeter wave radar are all used in different missile systems to guide the terminal phase, and each has different capabilities and vulnerabilities that make it suited to different target types and operational environments. The common principle is that the terminal seeker measures the angular error between the missile's current trajectory and the line of sight to the target, and the guidance law uses this angular error measurement to generate steering commands that drive the error to zero, resulting in the missile arriving at the target's position. The guidance law most commonly used for terminal homing is proportional navigation, which commands a lateral acceleration proportional to the rate of change of the line of sight angle rather than to the angle itself, and which produces trajectories that converge on the target with minimal maneuvering effort and minimal sensitivity to errors in the initial conditions of the terminal phase. The imaging infrared seeker represents the current state of the art in terminal guidance technology and is worth examining in detail because it illustrates how far the capability of missile guidance systems has advanced beyond simple point tracking. An imaging infrared seeker does not simply detect the target as a point source of heat against a cooler background. It forms a complete two-dimensional thermal image of the scene in the seeker's field of view, with spatial resolution fine enough to distinguish individual features of the target such as the engine exhausts, the wheel wells, the antenna arrays, or the crew compartment of a vehicle. An automatic target recognition algorithm running on the seeker's processor compares this thermal image to a library of stored target signatures and identifies the specific aim point that has been designated for the weapon, which may be a specific vulnerable point on the target rather than simply the center of mass. The seeker then tracks this specific aim point throughout the terminal phase, maintaining lock even if the target maneuvers, turns, or attempts to obscure itself with smoke or camouflage, and guides the missile to impact at the designated point with accuracy that in favorable conditions can be better than half a meter. This capability, called man-in-the-loop guidance for weapons, where a human operator can update the designated aim point during the terminal phase, or fire and forget for weapons that complete the terminal phase entirely autonomously, represents a qualitative leap in precision that was made possible by the combination of uncooled infrared focal plane arrays, high-speed digital signal processors, and pattern recognition algorithms that matured in the 1990s and 2000s. The aerodynamic control system that translates the guidance computer's steering commands into actual changes in the missile's trajectory is another source of precision that is often underappreciated. The guidance computer can calculate the perfect steering command, but if the control surfaces cannot execute that command accurately and quickly, the actual trajectory will deviate from the intended trajectory in ways that degrade the final accuracy. Modern missile control actuators use electro-hydraulic or electromechanical systems that can deflect control surfaces to commanded angles within milliseconds and with angular precision of fractions of a degree. And the control laws that translate guidance commands into actuator commands account for the aerodynamic characteristics of the missile at every point in its flight envelope, including the changes in control effectiveness that result from varying air density, varying speed, and varying missile mass as propellant is consumed. The design of the control law that stabilizes the missile's attitude and executes the guidance commands is itself a sophisticated engineering problem that requires detailed knowledge of the missile's aerodynamic coefficients across its entire flight envelope, and that has to be robust to the uncertainties and variations in those coefficients that exist in real flight conditions. The warhead and fusing system contributes to the overall accuracy of the weapon system in ways that are not always recognized as guidance problems, but that are equally important to the mission outcome. A missile that arrives within 1 meter of its target but detonates at the wrong moment, either too early before it has penetrated to the optimal depth for a hardened target or too late after it has passed through the target's critical structures, may fail to achieve the desired effect even though its guidance was perfect. Modern fusing systems use multiple sensors, including radar altimeters, contact sensors, and time delay programmable fuses to detonate the warhead at the precisely calculated moment that maximizes the effect against the specific target type. And the selection of the correct fuse setting for a given target requires intelligence about the target's construction, armor, and vulnerability that has to be incorporated into the mission planning before the weapon is launched. What the complete picture of missile precision reveals is that the accuracy of a modern guided weapon is not a single number that can be attributed to a single system or technology. It is the product of a chain of interacting systems, each of which contributes to reducing a different component of the total error, and each of which has been refined through decades of operational experience, laboratory research, and engineering development to the point where its individual contribution to the total error is smaller than any other component in the chain. The inertial measurement unit limits the mid-course error. The satellite navigation integration bounds the inertial error accumulation. The terrain contour matching provides position fixes in GPS-denied environments. The terminal seeker eliminates the residual mid-course error in the final seconds of flight. The control system executes the seeker commands with the bandwidth and precision needed to translate guidance accuracy into trajectory accuracy. And the fusing system ensures that the terminal accuracy of the trajectory is converted into the desired effect on the target. Remove any link in this chain, and the overall accuracy of the system degrades in ways that cannot be compensated by improving the other links, because each link addresses a different physical source of error that the others cannot correct. This is why missile precision is fundamentally a systems engineering achievement rather than the achievement of any single technology, and why the development of a new precision weapon system requires the simultaneous mastery of sensor physics, signal processing, control theory, aerodynamics, material science, and explosive engineering in a way that few other engineering endeavors demand.